I did.
Okay, sorry, we got to continue. If you want those answers, just come to my office hour. We can work them out. But I got like, 20 minutes to do the rest, so I may have to go fast, and I may have to skip the examples. But remember, these are online, so just go through, and I'll tell you when I've skipped an example, and you can go check it out yourself. So, very quickly, we just did two functions where we saw that there is behavior going to infinity, right? So I just want to give you the definition of what we call a vertical asymptote. Right, that's what a function heads to infinity. So the algebraic expression for that is when limit of x to a from the right to f of x is equal to positive infinity or minus infinity, and the limit as x goes from a to the left of f of x is equal to plus infinity or minus infinity, then the line x equals a is called a vertical asymptote. Okay, so for example, you had this guy, like 1 over x, has this, x equals 0, as an asymptote because you approach the infinity from either side. Okay, so now what I want to do is now allow you to work out these limits using algebra, as you want to do. Because you're not always going to be able to plot the function, right? You don't have access to Desmos on your test. So here are the limit laws. So this is for evaluating limits algebraically. Okay, this is sort of boring. I'm just going to write you a bunch of rules that you're allowed to do with limits. So it's going to make it a lot faster if I can say this. So suppose c is a real number. The limit of x goes to a of f of x exists and is equal to L. Let's say the limit of x goes to a of g of x exists and goes to m. Then what can I say? I can say that the limit of x goes to a of f plus g is just going to be L plus m, the sum of the limits. It's also the case that the limit of x goes to a of the product of these two things goes to the product of the limits. It's also the case, so this is me basically just explicitly allowing you to use algebra to solve these problems. What else do we got? We got limit of x goes to a of some function, some constant c times f is just c times the limit of x goes to a of that function. And maybe one more for the limit as x goes to a of f over g is equal to L over m, provided m is not 0. Okay, why am I telling you this? Okay, so there's an example that I'm going to skip. You should do it. Just take a look in the notes. I'm telling you this because of this. And this is the thing that's going to enable you to work in the way that you're used to working. So here's a proposition, which we're not going to prove. But this proposition is really important. It's called the direct substitution property. And the direct substitution property says this: if f is a polynomial, do you guys know what those are? Okay, polynomials are things that look like this. So if f has this shape, a0 plus a1x plus a2x squared, all the way up to n, right, such that these are real numbers and x is an indeterminate. So it's just like a quadratic polynomial is a polynomial. A cubic is a polynomial. So if f is a polynomial, or what I'm going to call a rational function, which means that you allow division and nth roots. Right, so you start with a polynomial, you're allowed to multiply and add them. You're also allowed to divide them and take square roots of them. If that's how you produce the function itself, then the limit of x goes to a, then provided a is actually in the domain of f, then the limit of x goes to a of f of x is equal to f of a. Okay? This allows you to read, just evaluate the function properly. And I'll show you what consequence now this has. One of the first questions I gave you today was this one. X squared plus 1 over x plus, was it x plus or x minus? Minus 1. What did we figure out the limit to this was? Remember, this was the line with the hole in it. Right?
0.05 was it?
No, this is the line with the, I think it was 1, right? This is this problem that I gave you at the beginning of class. It had this hole, and it was 1, 1. Right? And I know why that's drawn like this because of this. Watch. Limit. So we're not going to read it from the graph anymore. Limit of x goes to 1 of x squared plus 1. God. If I put a plus on the last one, that should be a minus. And I want it to be a minus so I can do this. Okay, so be careful. You have to write down this limit every time. If you do this, if you say limit of x goes to 1 of x squared minus 1 over this is equal to x plus 1, x minus 1 over x minus 1. This equal means equal. This is not equal to this. It's not. It's wrong. You can't write this. This is lazy. You have to put in this every time. Right? The limit of this is equal to the limit of this. It's not the limit of this is equal to this. I know what you're trying to write, but you have to write what has to be written. But in any case, so I give you a bunch of limit laws which are saying, look, the limit doesn't get affected by arithmetic. Okay? So we could just do arithmetic. Right? So this actually is a difference of squares that should set off alarm bells because you should know how to decompose that. Now I can just do this, which means we have the limit of x goes to 1 of x plus 1. X plus 1 is a polynomial. I just told you that we can evaluate the limits of polynomials just by evaluating them. That's this. So now I just say the limit is 1 plus 1, which is 2. Okay, so now you have an algebraic way of working out the limit, not just geometrically. But we actually had to say, look, you're allowed every time you add, divide, do something in particular, that will not have an effect on the limit. But mathematicians actually had to sit down and prove that this is possible, that doing this has no effect on the limit itself. And it turns out that it doesn't. So that's all you need to know. Yes, sir?
Isn't that a rational function though?
Yes, it's a rational
So
function.
it doesn't say like we could use it with rational functions.
It says right there that you can use it with rational functions.
Yeah.
If you put it in originally, though, what do you get? It's undefined.
It's undefined, yeah.
Right? I have to manipulate it first in order to...
Okay.
Look, this function, it doesn't matter that one's not in it. Right? Because I get 2. It's a new function, so. Okay. I'm going to use the illegal blackboard just to save some time. What do I got left?
Got 12 minutes.
12 minutes, okay. Okay, so here's, I want you to do this as an exercise then. Exercise. Find the limit of x goes to 0 of the absolute value of x. Just note that this always breaks up like this, right? So when x is bigger than 0, the absolute value of x is x. So you have this really. And you also have this on the other side. All right, so you can always break up absolute values like this. This is how you have to do it algebraically. So finish. Okay, the last thing I want to talk about today is this thing called squeeze theorem. Because you won't always be able to read off the limit nicely by manipulating the equation. So this is going to be, so this is your worksheet for today, which you're going to have to do at home. So the worksheet wants you to investigate this limit. The limit of x goes to 0 of x squared sine 1 over x. Okay? And you'll never be able to get it. You'll never be able to pin it down. This function, it has crazy behavior. Right? So what you're going to need to use is squeeze theorem. And this is the squeeze theorem. Okay, so here's two parabolas. Here's an upward facing parabola. Here's a downward facing parabola. They all go through the origin here. Okay? So the squeeze theorem says this. So what's the limit of x squared as I head to 0? 0. The limit of minus x squared as I head to 0 is also 0. So the squeeze theorem says this. Listen, you have a function up here, you have a function down here. If you draw another function in between here, that's always in between, okay, if this is f, this is g, and this is h, h now is squeezed in between these two curves. That means, and this is what the squeeze theorem says, okay? And this is important. So I always write these theorems that you're going to use like this. Provided, like, so you've got to see these theorems as like crossing bridges. And before you can cross the bridges, you have to pay the toll. You can't apply a theorem when it's not applicable. So I'm always going to write provided. And these are the things that you have to check off before it's legal to use that theorem. So provided f of x is less than or equal to g of x, which is less than or equal to h of x. I think I maybe have mislabeled this. This should be f, this should be h. This should be g. Okay, so provided g is actually caught in between these two functions, and provided the limit of x goes to a of f is equal to the limit of x goes to a of h, right? So the limits of both of these functions have to exist, have to be equal. Then this doesn't always have to be the case. This only has to be the case near a, then it is the case that the limit of x goes to a of f of x is also L. Okay? So basically, that's the algebra. Here's the geometry. If you have two functions and you can squeeze another function through a point, it's important that these functions touch. Right? It says nothing if you manage to squeeze it through here. Okay? It's yes, sir.
Do you mean g of x in the lower line?
Yes, I do. Thank you. Okay. All right, so here's the function g. It may be crazy. It may have some like crazy complicated expression, but as long as you know that it's bounded above and below by two functions that eventually touch, so you have to exclude this, they certainly touch, all the limits have to be equal. This should be clear. You're stuck in between two curves. Right? So if you can upper bound the curve and you can lower bound the curve and you can make them touch at the point where you want the limit, you can read the limit. The limit of this crazy curve here will be 0 because it's trapped. Okay? So your task, your worksheet, is to demonstrate that this has a limit using the squeeze theorem. And you're being walked through it, the steps. Okay, so that's what I want you to do. And I guess I'll give you a couple exercises, and then you can get out of here.